Okay, my name is Jong-won Kim. I'm a professor at the Department of Mechanical Engineering of Seoul National University. Today, at Chapter 6, I will talk about product drawing principles for dimensioning, right? In last lecture, I explained the product drawing principles for shape description. So, in parts drawing, shape must be made perfectly, but without any dimensioning, then nobody knows what size it is, right? So dimensioning is also very important part of product drawing principles. Okay. So in Korean language we call it 치수기법. Okay. All right. Firstly, I like to remind that we have to use the general tolerance, which we call it 보통공차 in Korean language. So I believe that you remember that in your title space, the general tolerance must be included, all right? So according to this general tolerance, so if you place a dimension 25 like this, then the meaning of 25 in the drawing is to machine it as 25 plus minus 0.2. So plus minus 0.2 is added according to this general tolerance. So you see, 25 is within this range, 6 to 30. So plus minus 0.2 is applied. Okay, all right. So plus minus 2 is from the general tolerance of the title space. So the length of the parts machined by the dimension 25 here, 25 are normally distributed as follows. So normally distributed, okay? And the average is 25.0. It means that if you manufacture the parts, for example, 10,000 units, 10,000 parts. It's a huge number of parts, right? It's mass produced. 10,000 parts. And every 10,000 parts, you measure the dimension 25. Then it will within 25 plus minus 0.2, okay? So it means that 24.8 to 25.2. But mostly 25.0, the parts whose dimension, real dimension is 25.0, the number will be very high, right? And the distribution would be like this. But this is very ideal case. So I will actually this distribution is not like this. I will explain it at the blackboard. Okay, all right. So actually 25.0 here, and the tolerance, upper tolerance plus 0.2, and lower tolerance minus 0.2, right? So actually the average is not like 25.0. The many parts, maybe average would be like here, not 24.0. There are so many parts concentrated onto the somewhere between plus minus 0.2. So there are so many parts here, and then it is distributed worse than normally distributed. So it is a little flat. Distribution is more flat. comparing to the normally distribution. This is a very ideal case. Normally, mostly the average is not 25.0. It is between plus minus 0.2, and the distribution is more a little flatter than comparing to the normally distribution. This is a real case, actually. All right. Anyway, it's true that there are some distributions with this general tolerance. Okay. All right. Let's go to the slide mode. Okay. All right. So anyway, the general tolerance is very important. So general tolerance must be included in your title space of your drawing. Okay, and another aspect is that the general tolerance is accumulated. All right, it is very important concept. For example, this is a body and gasket and cover. So, and the body, the gasket is attached, and the gasket is the some part with the where the internal contents is prevent the internal contents coming out between body and cover. So gasket is something like a rubber, right? Very smooth material. So it is applied here, gasket, and cover is attached, and then the bolt. With the bolt is fastened to combine cover onto the body. Okay, all right. And so now this is the drawing of the part drawing for body. Okay, the body. So especially we see the dimension for the bolt hole, tab holes, right? A, B, C, D. Okay, and the dimension is that from A to it is 40, and it is A to C 80, A to D 120. Okay, so we place the dimension like this. Okay, and general tolerance here. All right. Now, if when you make a part drawing for cover, this is a case 1. Now, since you know that the dimension between each tab hole is 40, so simply you just place dimension like this, 40, 40, 40. Okay. Now, what's the difference between the dimensioning of cover and body? This is a 40, 80, 120. This is a 40, 40, 40. Now, it is very important that the general tolerance is accumulated. So, for example, A to B, 40. So, in general tolerance, 40 means this range. 40 is within this range. So, plus minus 0.3 is applied. 40 plus minus 0.3. Also, B and C, 40 plus minus 0.3. C to D, 40 plus minus 0.3. So, from A to D, the general tolerance is accumulated. So, A to D, it is accumulated, so that 120 plus minus 0.9. Okay, actually, the tolerance, since plus minus 3, plus minus 3, plus minus 3 is accumulated. So A to D, sometimes the dimension can be 120 minus 0.9, and sometimes A to D, the dimension may be 120 plus 0.9. Okay, it's possible, since the general tolerance is accumulated. General tolerance of plus minus 0.3 is accumulated 3 times. So, okay. So A to D, 120 plus minus 0.9, actually, okay? Now, looking at the dimension 120 of body, then since A to D, it is directly dimension like 120, so it is not accumulated. Just 120 is between this range, so plus minus 0.5 is applied, plus minus 5. So in the worst case, if A to D, the dimension is 120 minus 0.5, and in this case, A to D, the dimension is 120 plus 0.9, then if you body and if you overlap cover and for hole A, if you match hole A and then looking at the D, then sometimes the tap hole of the body and the through hole of a cover is overlapped. So the maximum overlapping is 1.4 millimeter. 1.4 millimeter is overlapped. So you cannot see the tap hole of the body entirely. It is just 1.4 is overlapped. Okay? So in worst case, if you imagine that this is just four tap holes, but if it has 7 holes or 8 holes in series, then maybe 8 holes, then the relation is if it is 8 holes, then plus minus 0.3 is overlapped 7 times, so plus minus 2.1 is accumulated. So in some cases, you cannot put bolt into the tap holes because it is overlapped very much. Okay, so that is the importance of the worst. That is the worst effect of the accumulation of general tolerance. Okay, so you should be very careful about it. So the best way is that you matching the dimensioning pattern, body and cover, 40, 80, 120. It's the same pattern, right? Same dimensioning pattern. So this is much better than the case 1, okay? To reduce the effect of general tolerance accumulation, all right? So I think that you catch the meaning of the accumulation of general tolerance, right? So it is very important. Now, this is an example of the general tolerance accumulation. So explain how much accumulation of general tolerance occurred to the distance only 20 between A and B, just 20 millimeter. But how much the accumulation of general tolerance? Now, this is 80. So 80 is how much? Plus minus 0.3. 40 plus minus 0.3 also. 60 also in this range, so plus minus 0.3. So from top surface of A to bottom, accumulation of plus minus 0.9, all right? Now 20 here, plus minus 0.2, and 180 here, plus minus 0.5. So total accumulation, this part, 0.7, plus minus 0.7. So plus minus 0.7 and plus minus 0.9. So total accumulation is that plus minus 1.6. Only 20 millimeter, but accumulation of general tolerance is plus minus 1.6. It is a huge accumulation of the general tolerance. Okay? All right? So please understand that the meaning of the accumulation of general tolerance. Very important concept. Okay? All right? And so maybe sometimes you may maintain the dimension datum of the body and cover is now hole A. Okay, hole A, from hole A, this is hole A is the dimension datum. So from hole A, 40, 80, 120 is the dimension is placed. Okay, all right. Now in A and B, part A and B, the shape looks very similar, but from the dimensioning, dimensioning is different. So sometimes the dimensioning, since dimensioning is different, so then it means many things. For example, dimension datum in A is the whole center A. So from A, 60, 25, 85, right? Okay. But in here, just the 25, 60, and 25. So there is no specific dimension datum. So the dimension datum is not fixed in part B. Okay. Now, and the tolerance of the hole in B. Now, pi 40 plus minus 0.05. This is in part A, pi 40 plus minus 0.5. So it's much, part B is much accurate, right? Much accurate. So this means that manufacturing procedures and methods of part A and B are different with each other. So manufacturing procedure means that for manufacturing this part, from hole A to hole B is assigned. It's the same. Hole A to 25 is assigned. Part B from A to 60 and 25 assigned. It's the same until this procedure same. But looking at the manufacturing of this edge, the procedure from this hole to 25 is assigned, and this edge is manufactured. But in this hole, this edge, it is manufactured from hole A to 85 is measured and manufactured. So manufacturing procedure becomes different between each other. All right? Okay? So only the dimension, since dimensioning is different, manufacturing procedure becomes different. Okay? All right? This is a very important concept. And also manufacturing methods becomes different between, since this is a more accurate tolerance. So machining this hole, maybe you may need a more expensive machine tool, right? Plus minus 0.5, maybe you can use very cheap machine to make it, since tolerance is a little large. But this is a very accurate tolerance, so you need a little expensive machine tool. That means what? Manufacturing cost becomes higher. In part B is more higher. Okay? Manufacturing cost becomes very higher. So manufacturing methods are different because of the different dimensioning. All right? It's very important. Okay. Now, this is locating dimensions by using datum. So this is a datum. So in the horizontal direction, this is the datum. So this is dimension. All dimensioning is from this datum, right? You can understand me, right? And B, this datum is in the vertical direction. This is the datum. So all datum, and in horizontal direction, this is a datum. In this case, even if it is the same shape, the datum is different. So in this case, datum is the center of this hole. So it is all dimension is from this datum. All right. Okay. This is the side face is the datum. All right. And since there are many holes, so and these holes are sharing one datum, then this is also very nice way of dimensioning. So locating dimensioning. So from small circle, this is the datum O, and 1 and 15, 29, 51, 65, 87, 101, 116 is placed, and also this is the datum, and dimension is located using datum O. It's a very nice way of dimensioning. Okay, if it has one datum. Well, okay, and also this is, maybe this looks trivial, but this is very important, actually. Because this is 25, 60, 25, and 110 is, it is a duplicate dimension. So it is not allowed. It is not allowed. Why? If it is a duplicate dimensions, then it gives the technicians the confusion in manufacturing procedure. Okay? Since there are duplicate dimensions. All right? So if your intention is like this, then 110 is just the reference dimension. So it is it is expressed like this. So okay. So you have to avoid the duplicate dimensions by any way. All right. Okay. All right. The type of there are type of dimensions. The dimensions in A represent the size. So the circle of size is now pi 8. Okay. The size of groove 10. This is the dimensions in A represent the size, and those in B the position. So the position of two circles, 20, right? 20. This means 10. 10 is the position of the edge from the center of circle. So this is the position. So by integrating A and B together, so A and B, the size and position together, like in C, then the task of dimensioning is finished. Okay, all right. So this is the types of dimensions. So one represents the size, and the other represents the position. So, okay, and the format of dimension line and the extension line is here. So dimension line is parallel to the line where you want to place the dimension. So this is the dimension line is parallel to the feature where you like to place the dimension. 10 to 15 millimeter is proper, and maybe we can use closed arrowhead. It's generally maybe you can use closed arrow as the ending symbol, but this is open arrowhead. In Korean KS Korean standard, the open arrowhead is recommended, but mostly in every industry we are using closed arrowhead. So in this textbooks, I recommend, I always use the closed arrowhead. Okay, all right, and the shape of the arrowhead is to be the angle of the arrowhead to be 30 degrees. So 30 degree means that the arrowhead is a little flatter comparing to the equilateral triangle. Okay, the angle of the equilateral triangle is 60 degree, but you see, this is 30 degree. The angle is 30 degrees, so it's more length, more longer than the equilateral triangle. So it is recommended 30 degrees. Okay, right? Yeah, it's just since we are learning graphic language. So language, sometimes if the language is natural, it's the same story. So it is natural. 30 degrees is more natural. So you may keep that the arrowhead to be 30 degrees. It is recommended. It looks more professional. Okay. If there are not enough space, maybe you can use closed dots like this, which I will show you some examples in later slide. Okay. All right. And never use the visible outline or center line as a dimension line. This example. This example, this is very lazy. This is lazy guy is doing like this. Visible outline, you do not use it as your dimension line. So this is a very good way of making dimension line here, 24. Okay, extension line and dimension line. All right. And also in 8, the dimension 8, the center line is used as the dimension line, but this is not recommended. This is a good way of extend the center line as the extension line, and dimension line here, and 8 is placed. All right. Okay. And do not make it closed with the other overextension lines here. The dimension line and extension line is closed, so it is not recommended. So 15, dimension 15 here, and dimension 25 here, right? So it's a good way of dimensioning. And use a leader to place the dimension for circles. So this is leader, pi 10, okay, leader. So here 10 is placed like this, but this is not recommended. So this is a good way of placing a dimension for circles. Okay, all right. Pi 7, rather than pi 7 here, pi 7, this is more recommended. Okay, good way, all right. Okay, and the way of drawing the extension line, it is according to the common sense. So this is a dimension extension line, vertical to the edge, but this is not recommended. This is maybe it's a common sense. This is not real length of the edge. Okay, so this is not recommended. This is a good way, and from the dimension line, you may leave 2 or 3 millimeters longer, okay? And this is a special case. If it is inclined line, sometimes you make extension like this, extension line like this, but this is not many cases, not frequent cases. And extend the center line to make an extension line. This is a good way. And looking at the example of ENF, if it is more obvious to place dimension inside the view, you can use the visible outline as an extension line, as in example in ENF. Since ENF, the shape is a little longer and narrow, so in this case, you may use the visible outline as the extension line. So this is not frequent cases, but sometimes this is a good example that if the place is narrow and no enough space, then sometimes this is a good way of dimensioning, okay? So please refer to the good example. Okay, and also place dimension figures as plinth letters with same height, all through the part drawing. The widths may be varied slightly, but of course, maybe you are going to use CAD tools to make your part drawing. But even in that cases, you may obey the principles of placing the dimension figures. So, for example, place them in the center of the dimension line. So, dimension 30 is the center of the dimension line, slightly above the dimension lines, 36, right? Place them in the center of the dimension line. Then if no enough room, place them on the extended part of the dimension, like a 2. Since this is a very narrow space, so you may place the number 2 in the extended part here, like, okay? And in this case, this is the dotted ending symbol, okay? So arrowhead, no enough space for arrowhead, so you may use dotted line as an ending symbol here. And if since the space is very narrow, so you may use leader to place number 2 like this, okay? All right? This is, and the 3, the dimension 3, using the leader, so you place the number here, right? And the direction of the dimension figures, maybe it is the place dimension figures so that they are readable from the bottom, the 70, 10, 26, 75, all readable from the bottom, and also 30, pi 20, pi 30, pi 50, all readable from the right side. Okay, this is the very general way of the placing dimension figures, the direction, okay, from the bottom and from the right side. And for the inclined dimensions, like 39, then you may refer to this figure. So 39, 39, maybe the direction is similar to this. So 20 is here, so 39 is here. So, okay, all right. And for angle figures, maybe you can use either E or F. But I recommend you using F, all readable from the bottom, right? The angle figure, okay. All right. And how to draw readers? Draw the reader inclined by 45 to 60 degrees here. 60 to 45. It means that if it is more slight inclined like this, less than 45, then it looks not so professional. So I recommend the angle between 60 to 45. So, okay? And the direction is pointing to the center of the circle, okay? All right? If the leader begins from the feature boundary, add an arrowhead at its end. If it is inside the black dot is applied and leader line is connected. 오늘 왜 이렇게 목이 마르? 목이 건조하세요? 네. 자, 다음에. Okay, now when locating dimension figures, use properly both the parallel dimensioning and the series dimensioning. So this is a parallel dimensioning. So it has the datum, dimension datum here, and 150, 420, 640 is placed using the, so we call it parallel dimensioning. And series dimensioning is, there is no datum anywhere. So it is just in series. Okay, the dimension is just in series. So in series dimensioning, of course, the accumulation of general tolerance is possible. Okay, 15, 14, 22, the general tolerance is accumulated. But if you are looking at the function of the part, even if the accumulation of general tolerance is possible, if the function, looking at the function of the part is okay, then you may use a series dimensioning, because it's very simpler way of placing dimension. So anyway, the parallel dimensioning and series dimensioning is all together. You can use both parallel dimensioning and series dimensioning together. Okay, so if you at the part drawing, if some part in some area, if you're considering the function of the part is okay, then you may try a series dimensioning, and in the other area, looking at considering the function of part, the data datum must be placed, then you may use parallel dimensioning. Okay, all right. So you can use both properly, both dimensioning method properly in your part drawing. All right, and this is accumulative dimensioning. So maybe I explained it in previous slide. So this is the datum O, and all dimension from this datum, 15, 29, 51, 65, right? So we call it accumulative dimensioning. And this is a coordinate dimensioning. So X and Y, the datum is here, and there are many circles in one plate. There are many circles. Then the coordinate dimensioning is a very nice way of place dimensioning, right? So A, B, C, the circle symbol here, and X and Y coordinate, and also the diameter here. Okay, this is very, very nice way of place dimensioning when a plate has so many circles inside. Okay, and this is the A, and looking at A and G. A is here. Pi 50, pi 140, A, and A here, pi 50, pi 140, A, okay, and G here, G, pi 70, pi 80, right? Place diameters in the side view by using the symbol pi. Side view means that of course, this is the front view, and this is a side view. So don't confuse at the meaning of side view here. So this is a front view, of course, and this is a hatching line. So this drawing is a section drawing, which I will explain it later lectures. Anyway, the front view is made using section view. Okay, and this is a side view, but side view, if there are some persons who notice it or not, but this side view is just made only the part of the this area. Only this area is projected here. So if it obeys perfect projection, then maybe there are some features should be drawn here, which is the area of this is projected here. But this is just this area. Only this area is projected here. So we call it this is a partial drawing, which I will explain it next lecture. So partial drawing here. So anyway, this is a side view and this is a front view. Okay. Now, looking at the dimension of diameter, where it is placed, it is in the here, not here. So pi 50, this is pi 50, so the pi 50 is not made here using the leader and pi 50. This is not recommended. Pi 50 is placed at the lateral view. Okay, pi 50 and pi 40. This is only pi 40, 150 or 140 here. So the dimension of 140 is placed here using symbol pi. Okay, only the 10, 100, the diameter 100 is implied for the pitch circle. So only the pitch circle, the diameter of pitch circle is placed at here. Okay, all right. So usually the diameters, the dimension of diameters is placed in the lateral view, not at the front views. Okay, not at the view which is see the circle directly. Okay, it is placed here. And right, the place directly the pitch circle diameters here 100 inside the circle. Only the pitch circle is placed directly onto the circle, right? And 4-20 drill means that there are 4 pi 20 drill holes. So, for example, 4-20 drill. This means drill. Means that there are 420 pi 20 drill holes. So 1, 2, 3, 4. This means symmetric, which I will explain it later. Symmetric. So, okay, and 6-20 drill. 1, 2, 3, 4, 5, 6 drill holes. There are 6 drill holes. All right. Okay. And there are principles to locate the dimension figures. So locate the dimensions intensively on the front view. So this is the front view. So 50-30 is located intensively on the front view. Here, 50 and pi 30 is located intensively on the front view. Okay. Then locate the other dimensions on the top and side views. Okay, top and side views. So, all right. So, and also there are very important way of dimensioning holes with note. I will one by one. So 8-11 drill means that there are 8 pi 11 drill holes. Since depth does not follow it after the drill, after the latter drill, no depth follows. So depth does not follow after the drill. It is a through holes. It is a through holes. No depth. It is a through hole. Okay. So now looking at this 10 drill. So 10 drill. No depth follows it. So 10 drill means that it's just through holes. 10 drill. Okay, you understand that? So 5 drill, DP means depth. DP 15. So drill has 5 drill. So 5 diameter 5, and the depth H is 15. So depth is 15. So you may see small triangle here. So that's naturally followed from the shape of drill. So if a drill end has the cones. At the end of drill, it has a small cone. So cone. So in the small triangle represents that cone of the drill end. So it has the natural way of presenting holes with its finite depth here. Okay. All right. Now this is the tab holes. So tab hole, it has thread inside the hole. So maybe you may sound confused here. So I will explain it using the blackboard. Okay. All right. Yeah. Now this is we say that this is M10. So M10 is metric thread. Metric thread with the diameter is not exactly 10, but around 10 millimeter diameter, and this is a metric thread. If you like to see the exact size of the diameter of the thread, then you may refer to the Korean standard, KS, okay, metric thread. So the representation is that this is the thick visible outline, and this is the thin line, right? Okay, and this is a visible outline, and it has a thin line is outside. Right? And it has a hatching line. So it means that it is a section view. So section view, I will explain it in later lectures. But anyway, section view. So maybe since you are the freshman, and if you see this drawing, maybe you may be confused. So this is actually this is a thread, tab holes. So since actual view is something like this. So since it's the thread inside, actually, if you are observing obey perfect projection rules, then actually it should be drawn. It should be drawn like this. So since it's an inside thread or thread here, so this is the perfect. This is a drawing which obey perfect projection rule. But since you make this drawing is very complicated, it consuming so much time. So actually, this is the abbreviation. This is abbreviation of this drawing. So just assuming that if you make this tapping hole, then firstly you make a hole through hole first using the drill, and then using a tapping tool you make a thread inside. So this means that this is the hole through hole to make a thread. Okay, so this is a thin line. Thin line represents the thread inside. Okay, all right. So this is the abbreviation of this perfect drawing. So this is abbreviation. So this means that this is a tap. Thread is machined inside the hole, real holes. Okay, this is a tapping. So maybe so in the slide, you may see if the tapping hole has some depth, then firstly the drill hole is drawn. So this means that some drill holes. So drill holes. For the first step is to make a drill hole, and then using the tapping tool, you make a thread until the with your desired depth. So this is the so this means the thread, like here, thread. So thread is here, all right? So this is represents the tap hole as an abbreviation of the real tapping holes. So let's turn into the slide. Okay, So now maybe you understand that the H means that the depth 15. Whose depth is 15? The thread. Depth of thread is 15. Okay. M5 is metric 5. So, all right. So M5 and the thread depth is 15. M5. Okay. This is through tab hole. Okay. All right. And now, yeah, 8 M10 DP, depth 20 means that there are 8 M10 tab holes and each depth is 20 respectively. Okay? I think that you understand this. And also, now I'm going to explain C-bore, counter bore or counter sink. Okay? So the abbreviation is C-bore, C-sink. Now, this is a counter bore hole and counter sink hole, right? So let's looking at the note, special note, 10 drill. Okay, 10 drill means that 10 drill. So that this is the size of hole is 10 here, 10, all right, and 20. C-bore 5 means 20 is the counter bore hole. This is a counter bore hole, and diameter is 20, and depth is 5. Okay, all right. So actually, this note is enough. The dimensioning of the counter bore, this is not recommended. This note is recommended. Please, the note is very important. This is not recommended. The dimensioning, the way of dimensioning, this is not recommended, okay? Please understand that this note is very important, okay? 10 drill, 20 C-bore, counter bore, 5, okay? Then now, maybe since you are the freshman of the mechanical engineering maybe you are wondering why this counter bore is important. So I'm going to explain it, that the importance of counter bore hole using the blackboard. Okay, let's consider. Let's assuming that this cylinder, this is rotating very fast, spinning so fast. Okay, and this is a cover, and this is a body. So you have to, even if it is spinning very, very fast, but you have to attach cover into the body. Then maybe you have to use some bolt. Okay, so bolt here. Maybe you can use many bolts, but I just show you the 4 bolt for combining the cover onto the body. Okay. Now, assuming that you attach 4 bolts to combine cover and body, and it is spinning so fast, then this bolt head is sometimes dangerous. So if it's spinning so fast, so you cannot see any bolt head. It is spinning so fast. So maybe somebody, the hand may be hurt by the bolt head. So it is very dangerous. So sometimes you may try this type of design. So the cover, you design the cover like this, which has the counter bore hole. So if you design cover like this, then you can, the bolt head is assembled like this. It is just, the bolt head is just inside the counter bore hole. Okay? So bolt head is inside the countable hole. So even if it is spinning so fast, there is no danger to make this bolt head is contacting with any hand or something like that, because the bolt head is just under the surface of the cover, using the countable holes. So this is the importance of the countable hole. All right? Okay. All right. Okay. Also, the countersink hole, it is a various thread. It is a thread. This is a type of the countersink hole is like this. So the function of the countersink hole is similar to the countable hole. All right? Okay. All right. So and since this figure, this photo, maybe I showed you at the first lecture, right? There are so many bolting which has the equal space around the hole, right? Equal space hole. There are so many cases where we are going to design equal space tab holes, okay, right? Like this here. Right? So many cases. You are going to design so many equal space tab holes or equal space countable holes, like this example. So in this case, the dimensioning equal space, the way of dimensioning equally spaced holes is just to use note 6-5 drill. And then equal space here, and 10 CBO5. So we make 10 CBO5. You may understand this. 10 CBO5 and 6-5 drill. There are 6 holes, and these 6 holes are equal space. That's it. This is enough. And only the pitch circle diameter 60 is placed here. Okay, 60, pitch circle diameter 60, and this is what? 8-M10 metric 10 thread, tap hole, M10, BP, depth 30. And then what? Equal space. This is enough. This is enough. Maybe I wonder you understand the meaning of the importance of this dimensioning, way of dimensioning for equal spaced holes. So I will explain it more using Blackboard. Okay. All right. Now in the equal space holes. So, for example, this holes here. Now, center line. I explained that the center line should be like this, which with the direction pointing to the center of the circle, like this. Now, shape is like this. Now you try to maybe you try to place dimensions for each holes. Then, if you do not understand the importance of the note equal space, then you may try to place dimensions like this. So, okay, right, and this. All right. Assuming that the center of the circle is the dimension datum, then you may try place dimension like that. Okay? Now, the pitch circle, if the pitch circle is 100, then you may place dimension 50 and 50 here. Okay? Then my question is that how we are going to place dimension here? Dimension here, here. Okay? Maybe this is a 52 tangent 45 degree, right? This is not finite number. Okay? Then you are going to place dimension like this. Okay? This is very absurd way of dimensioning. 50 tangent to 45. It is not professional. Then how? What is the proper way of dimensioning for these equally spaced circles? Now, the answer is on the slide. Okay? All right? Let's go to the slide. Now, this is the right answer. 8, M10, depth 30, and equal space. Equal space is enough for the dimensioning of these equally spaced holes. Now you can understand me? It is very important way because you are going to design many equally spaced holes in your part drawing. Then in that every equally spaced holes, the way of dimensioning is here, using the note, specific note, equal space. Okay? This is very important. All right. Okay, and dimensioning chamfering, maybe general chamfers are dimensioned by using the general dimensioning method. Why chamfering is important? At the first lecture, I explained that without chamfering, the edge is very sharp. So you may hurt your finger using the sharp edge. So sharp edge has to be chamfered. Okay, so this is a chamfering. So this is a general way of dimensioning for chamfers. So and you may also C2. You may symbol C using C2, C2, C1 is enough. Okay, all right, all right, and this is not frequent case, but sometimes in case the true length of the drawing does not match the dimension figures. So for example, the dimension, actually in the first drawing, this shape is drawn that at the time the dimension was 30, so actually this drawing make based on the dimension 30, but after that, some design change has occurred. So in the case you have to change the dimension 30 into the 25, then actually the shape is not matching the length of 25. So at the time, at the number of 25, you may do a small line, underline, so that it means that underline under the dimension figure. So in this case, the true length in the following drawing is 30, but if the required length is finally 25 after the design change, then underline is added. Okay? Then you do not need to make a part drawing from the beginning. You may just erase the number 30 and make the right number 25 and make an underline. Then that's enough. Now you need a practice. So this is a dimensioning example. Draw a part drawing of the part as follows. Yeah, this is a cylinder block. So what is the first step of making a part drawing? Now the first step is to select the front view, right? So since this is the automobile, so you may select the front view in this direction, right? This is the front view. Now, the second step is what? Reduce the number of views. So front view and maybe in this case, front view and top view is enough. Two view drawing is enough, maybe, right? And then, how about the dimensioning? dimensioning. What is the principle of placing dimensions? The first one is that concentrate all dimensions into the front view first, okay? In the front view first, and then on the top view, just add the remaining dimension. That is the general way of dimensioning. So the answer is here. So front view, or maybe the datum is the center of the circle. So 25, 40, 40, 40, 50, and 10, 25, okay? This is the datum, dimension datum, okay? Or dimensions are integrated onto the front view first, and then the remaining dimension is added, okay? And for tender means this, all right? This is the nice way of dimensioning. So now you need a practice. So this is the homework 7. So the following two parts are assembled with each other, the hub housing and hub shaft. And so you may need to make a two-part drawing. So one part drawing for hub housing and the other part drawing for hub shaft, and try to place dimensions. And at that time, maybe you may notice that which would be the datum, dimension datum, right? And two-part drawings for hub housing and hub shaft. The dimension pattern should be matching with each other, right? To avoid what? To avoid the accumulation of general tolerance, all right? Okay. And this is the homework 8. Draw a part drawing of the part as follows, and please place dimensions. So I say that I describe the shape, some shape here. So this homework requires you to place dimensions according to the proper note. Note is very important. Okay, which I explained to you at the equally spaced holes. The dimension is made by using note, okay, not real dimension line. So in this example, I place several notes here. So please refer to this note, and according to the slide which I explain you the proper note, please try to make a proper note on the part drawing. Please practice that, okay? All right, this has been the today lecture. Thank you.